Okay, good morning, good evening, and all. See now, we are discussing about already in previous classes. We discussed about differential calculus, uh, and in fact, we are discussing about the chain rule, the use of chain rule, and Euler's theorem. Yeah, this is the chain rule involving functions of two variables, and another one that is Euler's theorem I talked about. Yeah, Euler's theorem for homogeneous functions. We have done some problems and we continue on these concepts. We try to do some more problems and then we will move to the maxima and minima case. So we take up this problem that is in the previous class we have talked about u is given as sine inverse x by y, sine inverse x by y plus tan inverse y by x. U is given as sine inverse x by y plus tan inverse y by x. Then we need to find. So need to find x dou u dou x plus y dou u dou y. This we need to find. So if you look at this one, either we have to apply chain rule or Euler's theorem. Chain rule is here. See, this is chain rule for explicit functions, functions that are defined explicitly. That is like, see the case 1, z is equal to f of u and u is equal to some function of x comma y. In such a case, we have wrote the chain rule there. Similarly, the second option is if u is equal to f of xy and x and y are functions of single variable, then we have another version of chain rule. Similarly, when it comes to the third one, there is a function of two variables x and y labeled z, and we have each x and y are functions of two variables. For that case also we have chain rule. So in principle we have three versions of chain rule when we are dealing with two variables, functions involving two variables. On the other hand, we have chain rule for implicit functions also, that is mentioned here. And there is one more thing that what I told is Euler's theorem. It talks about homogeneous function of degree n. So if we are able to see the given function here is a function of two variables, if we are able to show that this is a homogeneous one, then we can direct, and if we are able to find the degree of this homogeneous function, where is the homogeneous function here? The homogeneous function, we need to check, in fact, this one. We need to check. Yeah, we need to check whether this function is homogeneous. Then without applying chain rule, one can get the value of this x dou u dou x plus y dou u dou y. So now see, for this to be a homogeneous function, what we need to do is that you need to check whether u you need to, one needs to calculate utx comma ty. So in this case, it is equal to sine inverse. See here, sine inverse. You have x by y. So tx by ty plus tan inverse ty by tx. In place of y, we are putting ty, and in place of x, we are putting tx. Now this is equal to, sine inverse x by y plus tan inverse y by x, which is nothing but, which is nothing but u of x comma y. So now we have observed that u of tx comma ty is equal to u of xy. So this can be further viewed as t power 0 into u of xy. So what we now have observed is that, therefore, u of x comma y is homogeneous of degree 0, of degree 0, of degree 0. Okay. So now we can apply the Leibniz rule, Euler's rule. What did that Euler's rule says? Therefore, x dou u dou x plus y dou u dou y is equal to, in fact, what did it, that Leibniz rule says? Nu, where n is the degree of the homogeneous function u of xy. So in this case, the degree is 0. So therefore, x dou u dou x plus y dou u dou y is equal to 0 into u, that is 0. So the answer is 0. This is a multiple choice question. So in that one, 0 is there. Yesterday I have shown the set of problems. Okay. So the answer here is 0. Now, if we choose one more problem, we'll see. A typical one, right? Good. See one more problem. So this example is over. Now they have given another one. In that case, u is given as log x square plus y square by x plus y. I think it is not square, right? X power 4, y power 4. And then it is given. Now we need to find x dou u dou x. See, whenever you find this, you please see whether Euler's theorem is applicable here. So what we have to do? We have to check whether this function is homogeneous. If so, of what degree? That if we are able to determine, then we are done. Then it becomes n into u. N is the degree of that homogeneous function. So to check that, the to find the check whether this is homogeneous, what we need to do? We need to find u of tx comma ty is equal to log tx whole power 4, I mean is equal to log tx whole power 4 plus ty whole power 4 by tx plus ty, because in place of x what we need to put tx, and in place of y what we need to put ty. So in that case, this results in, this can be further simplified to log t power 4 into x power 4 plus y power 4 by t into x plus y, which results in, so here there is a problem. You cannot say this is a homogeneous function. For that only I took this one, 4 by x plus y. You cannot take here. So you cannot claim anything here. On the other hand, so this is not, it is not. So what we will do is that, in this case, yesterday also we have seen this one. This is not a homogeneous function, but can we apply, if still you can apply Euler's theorem. How? So you can say here that what we have observed, therefore u of xy is not homogeneous. First of all, is not homogeneous, because you cannot show that this is equal to t power n into log x power 4 plus y power 4 by x plus y. You cannot show. This is not possible. So what we do, yesterday I have given, in the previous class I have given a hint. In such cases you can go like this. You treat v as x power 4 plus y power 4 by x plus y. Then you can easily observe that v is a homogeneous function. V is a homogeneous function. V is a homogeneous function of degree 3. Why? See here, it is very simple. We have seen that already. So we have v into v of tx ty is tx whole power 4 plus ty whole power 4 by x plus tx plus ty, which is nothing but t power 4 into x power 4 plus y power 4 by t into x plus y, which is t cube into x power 4 plus y power 4 by x plus y, which is further equal to t cube into v of xy. This is the reason to claim that v is homogeneous function of degree 3. That is the reason. So, from here, from the given condition, what is the given condition here? U is equal to log x power 4 plus y power 4 by x plus 5. So we are treating, we are we are considering this whole object, we are labeling that object as log v. So what can we say now from here? So yeah, therefore log, therefore u is equal to log v. That implies v is equal to e power u. V is equal to e power u. But we know that v is a homogeneous function. So what can we say? This implies x dou v dou x plus y dou v dou y is, the degree is 3 there. We have already observed that is 3v by Euler's theorem. This is by Euler's theorem. So now see, we want to rewrite, but what we are asked for, we are looking for this one. We are looking for this. We want to find this. U should be there in our expression, not v. So somehow we need to convert this into, we need to write this in terms of u. So this implies x into, okay, dv, this is chain rule here, we are applying dv du into dou u dou x plus y into dv du into dou u, just plus y into dv du into dou u dou y. See how we got this one? We got this by looking at the first case here. What is that first case? Yeah, the first, I'm sorry. Yeah, the first case, see, that is z is equal to f of u is equal to phi of xy, then dou u, dou z, dou x, dou z, dou y were expressed in terms of the ordinary derivative of z with respect to u into the partial derivative of u with respect to x. Similarly, the partial derivative of z with respect to y is ordinary derivative of z with respect to u into the partial derivative of u with respect to y. We are using that one here. So now what is dv du? dv du, that is the ordinary derivative of that is already here. It is the dv du here. See, if you want what is dv du, that is derivative of, so here dv du is same as e power u, is same as e power u. So this is now is equal to, yeah, you see in the top you have 3v, that we need to write, that is equal to 3v, that you have to write. So that implies, this implies x into dv du, just now we have seen. What is the dv du? It is e power u. So this is e power u into, I write in short, ux dou u dou x, that is y into e power u into uy is equal to, is equal to 3 into e power u, because v is u power u. So this implies e power u into xux plus yuy is equal to 3 into e power u. So this implies you require practice. In fact, to practice, you can get quickly the answers. Ui is 3. So there is a possible answer there. It is, you can get 3 there. Okay. So this is there in the, I'll show that document also. I'll show that document also. Yeah. So if you look at, we just now we have discussed about this question. See, eighth question. See the possible, sorry, not eighth, ninth, sorry, ninth question. So the answer is C here. The answer is C here. In a similar way, we can find the 10th question also, because you can easily see that sine inverse x square plus y square by x plus y is not homogeneous. On the other hand, x square plus y square by x plus y is homogeneous of degree 1. So you can get the, you by treating x square plus y square by x plus y as v, you can get the answer. So that is the 10th question. Now see, we go for example, yeah, you see here, we'll choose the 14th question. 14th question is, uh, u is, you see, u is given as f of y by x, and then we need to find x dou u dou x and y dou u dou y, and see what will be the possible answer. We'll see. Okay, so for this one you require, so 14th question we'll see. So what is the 14th question? So this question is complete now. So if we look at the 14th question, what is given in the 14th question, it is given as u is equal to f of y by x. So given u is equal to f of y by x, this is given. Clearly this is a homogeneous function, see here, because if you take, see, this u is xy, u of xy this is. So what is u of tx ty? It is f of ty by tx. So this is equal to f of y by x. This can be viewed as t power 0 into f of y by x. Nothing but t power 0 into u. So therefore, I mean, you can write u of xy. Therefore, u is homogeneous function, of degree 0. So directly you can make use of the Euler's theorem. Therefore, xux plus yuy is equal to nu. N is 0 here, u, so it is 0. So the answer here is B. It is B. So similarly, yeah, you can look at Taylor series expansion of sin x, uh, About x is equal to pi by x he is asking for. Taylor series expansion for uh, so here I in the slides, again if you look at the slides, if you look at Taylor series, that is a one variable case. Yeah, here Taylor series expansion is there. So about x is equal to a. Yeah, how we to write about x is equal to? So here you have to take, what is the question there? Yeah, Taylor series expansion of sin x about x is equal to pi by x. About x is equal to pi by x. So it is better to write like this. See, so we need a series in terms of x minus pi by 6. Naturally, it is x minus pi by 6. So if you look at that, the possible answer is C here. The possible answer is C here. Yeah, it is C. Because C, for sin x expansion, there is an easy way to remember that. See, if you remember e power x expansion, you can find all the, so e power x is 1 plus x plus x square by factorial 2 plus etc. You need to remember this. Sin x is x minus x cube by factorial 3 plus x power 5 by factorial 5 minus x power 7 by factorial 7 likewise. Plus minus it alters the sign. So, but he is asking for about pi by x, about, I mean about pi by 6, about pi by 6 here. Where is that? About pi by 6. So, if you, about x is equal to a, if they ask, about x is equal to a, then this becomes, see, the same thing becomes, the same thing if you want about pi, uh, I mean about pi by 6. So you need to write this plus minus, okay, you take sine of sin x derivative, that is I am writing it as first order derivative, but you compute at x is equal to pi by 6, that is very important here. Okay, then by factorial 3, by factorial 3 into x minus pi by 6, into x minus pi by 6 plus sorry, plus, yeah, okay, plus x minus pi by 6, no, sine x, you have to take the derivative. If I write like this, then you have to take the third order derivative, third order derivative here, third order derivative by, third is already over, so we need to take fifth order derivative by factorial 5 x minus pi by 6 whole power 5 will come now. Here I need to take third order derivative, third order derivative. So sine, for sine it is cos, and for cos it is sine, like that. So actually here you will get a plus only. So now see, if you take like that, then minus plus will come. So the answer will be you have that C will be the answer. C will be the answer here. So you need to check just in right in terms of x minus pi by 6 powers of x minus pi by 6. Okay. So now see Taylor series. Okay. Yeah, you look at this Taylor series expansion of e power x cos y at 0 0. Okay, this is another one. So what is given there? E power x cos y. E power x cos y. So what is given here? Given f of xy is equal to e power x cos y, and the point given is 0 0. This is the point. So whenever you have 0 0, it is Maclaurin series. It is understood. So our f of xy is this. We need to find Maclaurin series. Okay. For that you need to see, this is a function of one variable. I have given here. Yeah, right. This one. This is the look at the second bullet point. F of xy is f of 0 0 plus 1 by factorial 1 into x dou by dou x plus y dou by f 0 0, etc. Okay, now we will apply this. So first two terms we will find. So here, what is f of 0 0? F of 0 0 is e power 0 cos 0. E power 0 is 1, cos 0 is 1, so you have 1. Okay, now next you need to know what is x dou by dou x plus this meaning. One should know. Then in that form only, easy form only, I have given this. So see, he is writing like this. In the slide I wrote like this. The meaning of this is, you simply calculate x dou f dou x plus y dou f dou y, then you compute that result when xy is equal to 0 0. That is the meaning here. So what is dou f dou x here? See, I write dou f dou x here in simple terms. Dou f dou x is same as e power x cos y, partial derivative. What is fy? Dou f dou y. Cos y derivative is minus sin y. So minus e power x sin y. Minus e power x sin y. So at 0 0 we have to see. So what is the answer here? Is equal to x e power x cos y. X e power x cos y plus phi e power x minus sin y. But you are putting that at xy is equal to 0 0. Don't look at this part. Don't substitute here. Only it is better give clarity here. Okay. So you need to put that xy like this. See here, right? you need to substitute in this only xy is equal to 0. In this only xy is equal to 0. So don't substitute in place of x0 and in place of y0. They will be there. But in the other parts you have to 0. So this is, if you put a xy is equal to 0, 0 here, and here, see this box I'm telling, and in this box also xy is equal to 0, 0. Put that. Then this is equal to x into e power 0 into cos 0 is 1. So 1 plus y into e power 0 is 1, sin 0 is 0, so into 0. So you are getting x as the answer here. So oh, just wait. Yeah, no problem. So here, where are we? Side dislocation. Yeah, right. So yeah, this is x is equal to 1. So finally we got x. Now look at the second term. What we mean by the second term here? Second term is 1 by factorial 2 into x dou by dou x plus y dou by dou y whole square applied on f xy at 0, 0. Okay, that we need to see. So that part we will calculate now. So I rewrite this because so that no confusion will be there. No confusion will be there. Yeah, right. Good. So what we need to say here, x dou by dou x plus y dou by dou y. Here I am talking about what is the meaning of this. This meaning is simply x we brought from here. Then we need to calculate the other one. Just a minute, we have to. Okay, anyway, if we disturb that. Okay, we need to calculate now x dou by dou x plus y dou by dou y whole square acting on f0, 0. This we need to find. So simply you expand like this, x square dou square by dou x square a plus b whole square, like y square dou square by dou y square plus 2xy dou by dou square dou x dou y acting on f of 0, 0. That is the one here. Acting on f of 0, 0. So here we have already calculated fx fy. See, that is here. Now we need to calculate here What is fxx? Again e power x cos y, no change here. What is fyy? Minus e power x cos y now. What is fxy? fxy is minus e power x sin y. Okay, that is the one. So, right. Just I will rewrite here because we cannot go. So what we have observed above is fx is yeah, e power x cos y. Fx is e power x cos y. And fy is minus e power x sin y. And fxx is e power x cos y, that is another time fx partial derivative with respect to x. Fyy is minus e power x cos y. Of course, we need fxy is minus e power x sin y. So actually we need these things. We need, actually we need these things at xy is equal to 0, 0 to be substituted here. To get this. To be substituted here to get this. So at xy is equal to 0, 0, see, this becomes e power 0 is 1, cos 0 is 1, so this becomes 1. And this object becomes cos y is 0, cos 0 is 1, e power 0 is 1, so it becomes minus 1. While this becomes sin 0 is 0, so it becomes 0. Thus, this object is, see, you don't have dou square by dou x dou y. So you have x square into dou square f by dou x square at 0, 0. So what you will get, what we will get therefore, x dou by dou x plus y dou by dou y whole square at f0, 0, we mean x into, just now we have calculated fxx at 0, 0. So I mean x square into that one plus y square into minus 1. Because see here fyy is minus 1. So we have x square minus y square. Now see, that is the third term. So what we are getting now, therefore fxy is f0, 0, that is 1 plus 1 by factorial 1 into the first term we have calculated as x. First term we have calculated as x. And the second term is calculated as x square minus y square. 1 by factorial 2 into x square minus y square. Plus etc. So we have, the answer is one plus x plus 1 by factorial 2, that is 2 into x square minus y square. A is the answer for the 16th question. Likewise, this is Taylor series for e power x into sin y. In terms of xy means same question this. Of course, there they asked about cos y. Here they are asking about sin y. In a similar way, we can do it sin y also. We can do it for sin y also. So if you take that problem, okay, one more problem we do that also, then Taylor series will be covered. So in that problem, what is f of xy? E power x into sin y. The earlier problem, e power x into cos y, that is. Now it is e power x into sin y. So better you do one thing. We are in terms of, he is asking, express this, express this. In terms of powers of x comma y. That is what he is asking here. In terms of x and y, see here. Yeah, right. in powers of x and y. That's what he is writing. So you just do one thing. First calculate you write here clearly what is fxy, that is f is e power x sin y. Then write fx e power x sin y. So fx is e power x sin y. What is fxx? Immediately write e power x sin y. Then fy e power x cos y. E power fyy minus 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 e power x sin y. Then e power fxy e power x with respect to y cos y. After writing this, you simply calculate at 0, 0 what are these values. At 0, 0 what are these values. So at 0, 0, that is at xy is 0, 0. What is this value we are writing? Sin 0 is 0, so this is 0. Again this is 0, this is 0. Cos y is 0, so it is 1. Sorry, cos 0 is 1, so it is. So again this is 0. Again this is 0. And this is 1. So except fy and fxy, all the remaining terms are zeros. So you can now straight away write x dou by dou x plus y dou by dou y, which I have given in the formula, the slides, is, so dou f dou x, see dou f dou x means fx at 0, 0. Fx at 0, 0 is 0. Only fy is 1. So into 0 plus y into 1. That is the thing. Then x dou f dou x plus y dou f dou y. Here square is there. So what did I tell you? X square dou square by dou x square. A plus b whole square simply write. Y square dou square by dou y square plus 2xy dou square by dou f dou x, dou x dou y. Now you act on f0, 0. So this is, see, fxx, what is actually symbolically, this is fxx, this is fyy, this is fxy. So among the chosen ones, only fxy is 1 All the others are zeros. All the second order derivatives are zeros. So this is only 1. Fxy is 1. So this is coming as 2xy into 1. That's all. So now the series. Just look at what is f00. F00 also we have calculated, I think. Yeah, f00 is also 0. So required expansion plus 1 by factorial 1 into dou by dou y square plus etc. So this is further equal to first term is 0, second term is y. So this is y actually. This is y. Second term is y. One by factorial 1 into y plus 1 by factorial 2 into 2xy, because the third term is 2xy. The third term is 2xy plus etc. So this is equal to y plus xy plus etc. Right. Now see what are the options here. So A is, you have y plus xy is there. Y minus. So naturally he is also calculating the third term. The third term I mean here, you need to calculate this also. I'll directly write this whole cube. So this is acting on, so what it becomes actually, x cube a cube plus b cube plus 3ab square, 3ab square. So xy square dou cube by ab square, right? Right. Dou x dou y square, that is right. Dou x dou y square plus 3, okay, right. One is 3ab, that is xy into dou square xy will be there. So ab into, when you are multiplying with y, y square will come, good. 3x square y dou cube by dou x square dou y. Now this should act on f of 0, 0. Now this should act on f of 0, 0. So it is already observed that, see, when we go back to here, so here only thing is that you need to compute for this one, what is this, what is this third order derivatives, then this, then this, nothing else. We have all this, all possibilities here. That is equal to, I write here, go there, fxx with respect to x, see here. So e power x sin y, same thing here, e power x sin y. Okay, fyy, 3 y's. So look at fyy here. Look at fyy here. So sin y is there, cos y. So minus e power x cos y, minus e power x cos y. Okay, then fxxy. Fxxy means you will get e power x cos y. You can check how. You go to fxx. Yeah. And with respect to y, so cos y. And what else is left? fxyy. So you go to fyy. Now with respect to x, minus e power x sin y. Now at xy is equal to 0, 0. We need to find at xy 0, 0. So at xy 0, 0 means this is 0. This is minus 1. This is plus 1. This is 0. Now go to the top. So he says x, 3 x's, that is 0. So this becomes 0. 3 y's. Actually y cube is there. Okay, 3 y's. That is minus 1. Please see here, you have minus 1 here. So this object is minus 1. You will get minus 1. xyy. Where is xyy? That is 0. So this becomes 0. Now xxy. xxy is 1. xxy is 1. So what terms will remain here? Minus y cube and 3x square y. But minus y cube and 3x square y. Okay, minus y cube and 3x square y. So here 1 by 1 by factorial 3 into 1 by factorial 3 into what will remain? Minus y cube plus 3x square y. That remains. Remaining terms, fourth order will come. In the answer, they are not there. That's why we are leaving the possible answers. Yeah, here. So now the correct answer is, okay, we can further simplify this. Y plus xy plus 2 into x square y. See, sorry. So what we are getting at y plus xy plus minus 1 by factorial 3 into 1 by factorial 3 means 6 minus y cube by 6 One more term, 3x square y, factorial 3 is there, so x square y by 2. Here you have f of xy plus etc. But what is this f of xy? So now look at the possible answers. So see here, minus y cube by 6 is there. So the correct answer is D. Here D is the correct answer. D is the correct answer. Likewise, so we now so far what I have covered. So far I have covered, we have done problems on, from the problem set we have shared on I mean chain rule and Euler's theorem, application of Euler's theorem, Taylor series. These three things we have covered good number of problems. Okay. So, yeah. Where is this? I'll show just a minute. Yeah. We are here. We have done Taylor's theory, Taylor's and Maclaurin series expansion this slide. Euler's theorem for homogeneous functions and chain rule. Okay. What other slides are saying? Other topics, I mean. So extreme of functions of two variables. This is one more very important thing. Okay, very important. Extreme values. So, okay, before going to extreme values, we can also see some more examples. Yeah, in the same problem set that I will go to extreme values. Okay, but some more good problems are there in this one. Yeah, I am coming over to here. So what did we say? This is not clear. So Jacobian is also there. Now we'll cover Jacobian. That is better. So see, good number of problems on Taylor series are there. Please be, you have to practice that. For example, see, this is a good question. I talk about the 30th problem. What is total derivative of the function xy? Total derivative. See, total derivative means here. See, what is total derivative? First, you are talking about when we are dealing with functions of two variables, for example. So in such a case, we write the total derivative as df. It is nothing but fx dx plus fy dy. This is called total derivative. So if you want to talk about total derivative involving three variables, that is fx, y, z, in such case we have df is equal to dou f dou x into dx plus dou f dou y into dy plus dou f dou z into dz. So in this problem, our f of xy is xy. So our f of xy is xy. So the total derivative is f subscript x dx, that is dou f dou x into dx, f subscript y, that is dou f dou y into dy. So this is fx is y and fx is, so you have y dx plus x dy. So we have the answer here, y dx plus x dy, that is A is the answer. And in a similar way, there are more problems on, yeah, you look here. What is this? Oh, okay, y power x, this is. Good, we'll see this one. This is a good question. F of xy is y power x, how we will do? F of xy is y power x. How f of, when this is the one, you need to take care here, because better convert this into logarithmic function. So log f is x log y. Log f is x log y. Then see, you can apply, we may be interested in, see here, what we are interested here. It's talking about dou square f by dou x dou y. Dou square x by dou square f by dou x dou y. So first what we do is that we'll try to find dou f dou x. So if you apply dou on both sides with respect to x, simple. So this implies one by f dou f dou x is log y. Fine. Now we want dou square f by dou x square. Dou square f by dou x dou y. That is the thing we are looking at. Dou square f by, yeah, dou x dou y. So you do one thing. We'll do one thing here. You just apply dou by dou y of, okay, dou f, you have 1 by f, dou f by dou x, then you have dou by dou y of log y. Both sides again we are applying partial derivative with respect to y. So this implies you are using u by v rule here. So f into, with respect to y, so I write fxy dou square of by dou y dou x minus fx into, because we are doing with respect to y, fy by, you have f square, quotient rule this is. Now Dou by dou I of log y. Okay. Dou by dou I of log y is 1 by y. So this implies y into fxy minus fxfy is equal to f square. Okay. So, right, we try to express this. Okay. Right. We already found fx, I think somewhere here it is fx is found. Yeah, right. Fx is found here. I write here, you can conclude here fx as f log y. F log y. Similarly, you can also calculate actually fy. See, log f is x log y. Okay, log x is f log y. Log x is f log y. Is it right? That is where we started. Sorry, log f is x log y. Log f is x log y. Now, if you go with respect to y, is equal to dou by dou y of x log y. So, this implies, okay, 1 by f fy is equal to, now with respect to y we want x by y. Log y derivative is 1 by y. So, yfy is xf. Yfy is xf. Okay, right. So now see what is asked. He is asking dou square f by dou x dou y at x is equal to 2 and y is equal to 1. Just a minute. Just a minute. Yeah, now, right. So, right. If at x is equal to 2, y is equal to 1, we have to calculate. At x is equal to 2, y is equal to 1. This at this point we need to calculate. So, two observations we have. What are the observations we have? This is one important observation. Then this is another important observation. Then, yeah, fx is equal to f log y is another. So we rewrite this thing. Fx is equal to f log y. Fx is equal to f log y. So we have fx is equal to f log y. This is one observation. Into is there actually. The second observation is uh, yfy is equal to xf. Yfy is equal to xf. This is one more observation. The third one is here. Y into f xy. So y into xy minus fx into fy is equal to f square. Is equal to f square. Right, good. F square here. Now see. Now xy equal to 2, 1. From this one, what can we get? Xy is equal to 2, 1. So, yeah, right. Fx at 2, 1 is equal to, first, what is f value? F at 2, 1, that is 2, 1. What is f value here? F value is here. Where is f? Y power x. Y power x means, y power x means, yeah, y power x means 1, oh, sorry, 1 square, y power x, 1. So at 2, 1 is 1, that is fine. 1 into, again, log 1 is 0. So see here, 1 into log 1 is 0. So fx at 2, 1 is 0. Very good. Now, this one, yfy is equal to xf. So from this, y is 1. 1 into fy. I mean here at 2, 1 is equal to x into f. F already is 1. So x is to 2. So 2 into 1. So here fy at 2, 1. Fy at 2, 1 is, fy at 2, 1 is 2. Fy at 2, 1 is 2. Good. Fx at 2, 1 is 0. Fy at 2 1 is 2. Fy 2 1 is 2. Good. But also I want what is f at yeah, f at 2 1. F at 2 1 somewhere else I wrote. Yeah, f at 2 1 is 1. This is also better to write. Again, f at 2 1 is 1. F at 2 1 is 1. Good. Now, the third expression. From the third expression, we need to see. Wherever y is there, put 1. Wherever x is there, put 2. Okay. So, 2 into f into fxy. F is 1 into fxy. F is 1. F subscript xy. We don't know that. This we need to determine. Minus fx into fy. See here. Fx into fy is 0. Is equal to, good. We got already now the answer. Is f square. F is 1. So it is 1 square. So fxy is therefore good. Therefore fxy at 2 1 is 1 square by 2, 1 by 2. This is how we need to do. Somewhere else 1 by 2 should be there, but something is missing here. You please check once. It is 1 by 2 is the correct answer, because yeah, log 1. Log 1 will be 0. No question of. So fxy, dou square of by dou x dou y, 2 1 is 1 by 2. That is the correct answer. So see here. So far, what are the topics we have covered? We just will look at. We have done good number of problems on chain rule. We have done good number of problems on chain rule in this session, and applications of Euler's theorem we have done good number of problems. Thereafter, we have done on Taylor's and Maclaurin series for one and for functions of one variable and two variables. We have done good number of problems, and how to compute different order derivatives when we are dealing with functions of more than one variable. For example, this problem also we had done. So we had covered when it comes to partial derivatives. When it comes to partial derivatives, calculus involved differential calculus. Only thing that is left to be discussed now is Jacobian, the idea of Jacobian, and Jacobian and maxima and minima. Those two things we need to cover. Okay, some more problem Jacobian, and before going for that, okay, you see here, this is another question that is given in GATE. So u is equal to log e power x plus e power y. Good. This is also again problem involving partial order derivatives. So u is equal to log e power x plus e power y. Okay. log e power plus x plus e power y. Fine. Now, what did they ask for? They asked for ux plus uy. U subscript x means dou u dou x plus dou u dou y. Okay, so you have ux is e power x by e power x plus e power y. Uy e power y by e power x plus e power y. So, ux plus uy now is nothing but e power x plus e power y by e power x plus e power y. It is 1. So, this is a problem involving the computation of partial order derivatives. This is a problem involving the computation of partial order derivatives. One more we will see. Good. This is xy log xy. Xy log xy we want. Okay, good. Xy log xy. Another problem. So we have z is equal to xy log xy. So what is zx? Dou z dou x. So we have xy by xy into y plus, okay, plus y log xy. This is UV rule we are applying, product rule. Similarly, zy is equal to xy by xy, okay, into x plus into x plus, with respect to y we are doing x log xy. So from these two things, we get zx is equal to y into 1 plus log xy, y into 1 plus log xy, and zy is x into 1 plus log xy. Now we look at the alternatives there. So x into zx plus y into zy. He's talking about x into zx plus y into zy. No, it cannot be equal to 0. That is not the possibility. Then A is not possible. Y into zx is equal to x into y into zx. X into, no. This is also not possible. B is also not possible. X zx is equal to y zy. We'll see this. X zx. X zx is equal to y zy. Yeah, that is right. So here x zx is equal to y zy. Right. Because what is x zx? Xy 1 plus log xy. What is y zy? Xy into 1 plus log xy. Thus, we have xz is equal to YZ1. This is possible. That is the third is the correct answer here. C. C is the correct answer. So this is there. Now some more involving partial derivatives may be good, I think, because I think we can have another session. We can have another session on Jacobians and uh, extreme values. I mean, see here, there are two more topics on differential calculus here. Yeah, this is the one more topic, extreme values of the functions of more than one variable, idea of Jacobian, and dealing with I mean transformations, that is, and some properties and applications of Jacobian. If we complete these two topics, then we can enter into the integral calculus and the related ideas So we just look at some more typical one or two couple of problems on computations. Yeah, this we have done. Taylor series also we have done. This also we have done. This is Jacobian. I think we have done good number of problems. We have done good number of problems. This also we have done. Right, good. On Taylor series, we have done sufficiently good number of problems. Yeah, I think this also we have done. Sine inverse we have done. Good. We have covered almost all problems here. So for now, we today, yeah, right. We have covered what are all the topics so far we have covered. I'm telling you here. One is computation of computing partial derivatives. Partial derivatives. That is, then we have applied chain rule sometimes, and sometimes we have applied Euler's theorem for homogeneous functions. Euler's theorem for homogeneous functions. All right, and then we discussed about Taylor series and Maclaurin series. Taylor series prominently. Taylor series and Maclaurin series. Good. So these are the topics we have discussed today. Simple computation of partial derivatives, chain rule, and yeah, Euler's theorem, and Taylor's series. So in our next session, hope we will cover these two topics: Jacobians, the idea of Jacobian, and extreme values. Then we will enter into the integral calculus part. So that is all for this session. Okay, thank you. So yeah, right. We have almost covered 15 slides. 14 slides in this presentation. Yeah, right. So for today,